Good evening, peeps. Good evening. So, what's that? Not buds. LIGO. Good evening, Absurdity fans, flat earthers, everyone.
LIGO stands for the Laser Interferometer Gravitational Wave Observatory.
Laser. Interferometer. Gravitational waves. Observatory. So we can have a little listen as we go along.
LIGO is really two observatories that work in unison in tandem. The LIGO interferometer has arms that are about 2.5 miles long, 4 kilometers. We have a laser. The laser produces the purest light you can possibly make. It produces light that's so coherent that it's capable of detecting gravitational waves.
We have these very massive mirrors. They weigh 40 kilograms, which is 88 pounds. They're about this thick, and they're just the purest material you can imagine.
The NSF, of course, had to be the source of funding for anything that would be as expensive as this.
This was going to be a very high-risk experiment. It was from its very inception.
If you think about this in the 70s and 80s, I'm amazed at how bold it was to do this, and visionary. It was bold and visionary. There's no other way to describe it.
NSF management, the National Science Board, they had to really step up to that. And they had a lot of discussions, brought in a lot of experts. There was great debate going on. But in the end, the people who thought it could be done won the day, and they went after it.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
And a ripple in the fabric of space and time, the same way as a ripple on a pond is a ripple in the shape of the surface of the water.
Nobody really believed that you could ever detect them because the size of the effect is so small. 1,000th the diameter of a proton.
Even Einstein himself never thought the detection would be possible.
I tried to do this back in the 1960s when I was a student. We couldn't make any progress. We didn't have the technology.
The idea was extremely simple, and it turns out to be the basis of light. What the gravitational wave does, it stretches space this way and compresses space that way. So you exploit that property. Put one object here and another object over there, and let the gravitational wave go through that system, and it'll change the space between these by contracting that one and extending that one. And I came to the conclusion that if you make this long enough, if you didn't make it a little pipsqueak thing like this, but if you make it sort of kilometer scale, you could probably get these extremely precise measurements.
1994.
Nobody had ever made something like this before, so there's a lot of technological challenges that needed to be overcome.
The precision that was required, it was just amazing, mind-boggling.
The MIT group has typically concentrated on developing new techniques to make the instruments work, and then to work on also data analysis algorithms that are well informed by the understanding of the instrument.
We have
observe gravitational waves from two black holes forming a larger black hole.
Two black holes merging together, literally nearly the speed of light, to produce a bigger black hole. How cool is that?
I said, holy mackerel.
This is the beginning of a whole new way of studying the universe.
It's monumental. It's like Galileo using the telescope for the first time.
Galileo.
Every time we have pointed a new instrument into the sky, nature has revealed secrets to us that we haven't known before. And so I feel very confident that this is just the beginning of such an era for gravitational wave observations as well.
Who knows what we'll see?
I would love to see Einstein's face if he could read this article that we just put out. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equation. Just imagine that. To me, that's a miracle that happened. Man's thinking, and also all the elegance, not only in the theory, but the elegance in the experiment. I mean, that is a human endeavor that I think everybody in the world should be proud of. I had to tell you that.
Black holes orbiting each other, nearly at the speed of light. Nearly at the speed of light. Huh?
In the early decades,
we're talking massive black holes, okay? These ones were 1.3 billion light years away, right? 1.3 billion. And they joined and they made one. And as that happened, the shockwave, right, goes faster than this though, yeah? And then, what is it, Louisiana and, where's the other one? Louisiana and Washington, alright? So they pick up the gravitational wave and it tells them, well, told them it was 1.3 billion light years away. That's how long these gravitational waves have been travelling, okay? The LIGO, the Laser Interferometer Gravitational Wave Observatory, picked up. Now, it started in 1994 and went into the 2000s, but they didn't really find anything. So in 2010, they shut it down, right? Closed, boom. But they closed it down in 2010. No gravitational waves were ever detected. The years passed, tick tock, tick tock, tick tock, tick tock. Sorry, was that around tick tock time? I don't know. 2015 or 2014. 2014. They opened up a refurbished LIGO. Refurbished, right? Been down for 4 or 5 years. They cranked it up and in the initial phase, just making sure everything was working, right? A signal, they picked up a signal. Ding! And all hell broke loose. 2014, the legal signal. And it had all of the properties of 2 black holes, right? But this signal only lasted, I think it was just a matter of seconds or something, And what it showed was that two black holes had been orbiting each other near the speed of light and ended up as one. Now this signal was picked up purely by chance, right? This has been going on since, that's when it started, in the 2000s. It was going hard up until 2010. It closed, they shut it, refurbished, no good, it's not happening. And then 2014, 10 years ago, they cranked it back up, a refurbished LIGO, and within minutes, right, this thing's crazy, within an hour, not in proper working mode, just going through all the cobwebs and everything, signal. Now, they weren't sure for ages, right, because it just seemed so unbelievable. And not just the fact that they picked up a signal, right? But we're talking about two massive black holes, okay? Now this occurrence is approximately 1 in every 10,000 years this happens. Right? You have to, I'm getting the numbers from them. So it's very rare for such massive black holes to orbit each other and end up becoming one. So that's one thing. It just so happened, this gravitational wave, right, that Albert Einstein wrote a paper on between 1916 and 1918. This gravitational wave was the last of physical evidence needed to solve one of Einstein's last theory that hadn't yet been proven physically, right? Of the relativity, super relativity, the general theory of relativity. The last of the physical evidence needed, right? Now that in itself is pretty amazing, right? So they had this thing running, carried on 20 years, right? Nothing, they turned it off, refurbed it, updated stuff, threw it back on in 2014 or 2015, and they picked up a signal immediately, right? A signal that is a 1 in 10,000 year occurrence. They picked it up, pure luck, right? Because those odds, right? And not only that, it was the last of the physical evidence that was needed. It was the last of Einstein's theories to do with relativity that hadn't been proven. Bang, look, another tip. 2, what are the chances? Now, there was a big thing where they were saying, oh, somebody set us up, and somebody been messing about with the programs and they're winding us up, because this is just too freaky, right? And this thing went on and on and on, and there's such a thing. It was, I mean, we've never seen anything else where they've actually looked at themselves and said, guys, is anybody messing about here, right? But it's just got on and on and on. Like they really drilled it home to make sure the public knew that nobody had tampered with the results. But it was such a push. You have to watch it to get a feel for it. And now these gravitational waves are going to become a new, well, they already are, aren't they? Because this was back a few years ago now, a new method of science, a new method of observing the universe. Now, it's just so amazing. I mean, how would they know that it was 1.3 billion years old, these gravitational waves, right? That's one of my first questions, how? How would they know? I mean, they're already on about maybe somebody's fed one into the program. So, I mean, how old would that one be? Would it not come up 10 minutes old? Like, brand new. If they can detect that, what would come up on the other one if somebody had fed something into the program? And then, you've got the speed of light thing. See, this is now, this gravity and the speed of light, gravitational waves and the speed of light are supposed to travel at the same speed. Look, light is absolute. It's massless, there's no mass, nothing. Gravitational waves, right? It's a shock wave, it's a physical movement. So, how can it go as fast as the speed of light? That isn't logical. Gravitational waves, it's actual friction, that's what it is. It's a light is just going to go straight past it, isn't it? It's the odds on those things. And if they're detecting these kind of gravitational waves, and this thing can detect, they reckon, an earthquake on the other side of the planet, right? This interferometer. So, would it not be getting just gravitational waves from loads of stuff, from everything in the universe, in fact? Because with shock waves, they go out, we'd be getting shock waves. They'd be getting so many gravitational shock waves. How would they know where to start? You're telling me it was quiet, no shock waves for 10 years. And then, so what's been happening in the universe for this 13 billion year old gravitational wave? I mean, how does that work? Billion years old. That's how long it took to reach Earth from where it happened. 1.3 billion years old. I don't know. Well, it's a big no for me anyway, because of light being absolute. So that 1.3 billion years, it's basically not really 1.3 billion years. Our eyesight will go to reach any light source in the night sky if it's bright enough. Instantly, like you go outside, you can look at Proxima Centauri. So he's looking that way. Doesn't look like it, does it? He's looking that way. You go out in the night sky and you look up at Proxima Centauri, you go, bang! It's bright enough. It's a light. It's a source of light. It hasn't been travelling for all that time. It's illogical. We look up and we see the source. Why is it going to travel towards our eyesight? Where does it stop? Here. What happens? Or does it stop on the pupil? Right? Our eyesight goes straight to the source. It's logical, isn't it? Like if you can see Jupiter at night or Saturn with a telescope on without, right? Your eyesight is not going to something that was there 90 minutes ago or something, because we see at absolute speed. It doesn't matter how far away something is. If it's nighttime and a light is bright enough, you're going to see it. The end, right? If you can't see it, it's not going to be there tomorrow because it's still traveling. It doesn't work like that. It defies common sense, right? If you're going to see a light that's in the night sky, you see it immediately, right? The end. Why does it? It's obvious, isn't it? We can see stars that are how far? Alexa, what's the furthest star we can see with our naked eye?
From
Cassiopeia.
The farthest star we can see with our naked eye is V762 Cass in Cassiopeia at 16,308 light years away.
16,308 light years, right? Cassiopeia. So I know, isn't it? Cassiopeia or whatever. Anyway. With the naked eye, you go out there and go, if you know where it is, go, oh, there, right? Because it's bright enough. That's the furthest we can see, right? But not because of our eyesight, because of the strength of the star, right? All other stars, it wouldn't surprise me if there's one or two that they've missed, but its brightness reaches us from that distance. You can see it, right? Now, if it was the size, Alexa, how big is Cassiopeia?
From helpingwithmaths.com, Cassiopeia is the 25th largest constellation in the sky, stretching across for around 598 square degrees.
598 square degrees. All right, I'm not even going to attempt to go there. Right, so it's massive constellation, right? Now, we look up, bang, there it is. If it were half the size and half of the wattage, dimmer, we wouldn't see it. It would still be where it is at 16,000 light years away, but we wouldn't see it, would we? Because it wouldn't be bright enough. Now, what else is there to say? You think we're spinning on our axis, so when I look up at the night sky, see it like Proxima Centauri, it goes, lose it, obviously during the morning, but then at night again, and it's just slightly moved, right? But you see it in the night sky, because we're twisted. Oh, you can follow it. Go that way, right? How there is no delay. I'm seeing one point there, then it's there, then it's there, then it's there, then it's there. And over the hours, it just moves right round. So if there was a delay, would you not get like a where's? Surely you would, wouldn't you, if there was a delay? It would be like a vroom, 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 vroom. So we actually see solid light, wouldn't we? But where it's turning. If it's taken that long to get here, it's just ridiculous. I tell you, when you look up at Jupiter from Earth, that it's already, Alexa, how long does it take for the sunlight to get to Jupiter from the sun? Is it 43?
From answers.com,
And then
it takes about 43 minutes for light from the sun to reach Jupiter.
so we say 8:20. So sun to Jupiter's 43, and then all the way back to us, which is another 35. So we're looking at 78 minutes. Right? So that's Jupiter. Here's the Sun. And here's Earth. Say there. Right? Not to scale. So they say that when you look at Jupiter, you look that way, right? But the Jupiter you're seeing, it's 78 minutes old. That's what Jupiter was doing 78 minutes ago. It takes the Sun 43 minutes to hit Jupiter, and then it will be 43 minus the 82, won't it? All the way back to us. Boom. I should have put Earth, put it up there. So, it's ridiculous. It just doesn't make sense. We can see Saturn, Jupiter, with our naked eye at night. With the naked eye, right? What about during the day? I mean, no, I suppose it's still the light from the sun, but this is illogical, right? It just is. There's no evidence for it. When they're looking up at the eclipse, is it ever mentioned? Do they ever say, well, considering that the sun is 8 minutes and 20 seconds away from where it actually is, this is quite an incredible eclipse, ladies and gentlemen. Do they ever say that? No. Well, of course they don't. When the planets are lining up, when you can see Mercury, Venus, Mars, Jupiter, Saturn lined up in the night sky, do they ever say, oh well, Jupiter's not there. Jupiter would be about over here, and then we've got Saturn would be over here, and then do they ever say that? No. And of course, the one fact about all of this, which it's so ridiculous, people, you're going to kick yourselves one day. Sun diameter 1,390,000 kilometers, right? Speed of light 299,792 kilometers per second. If we divide, I don't know how many times I've done this, we divide the sun's diameter by the speed of light. That's the speed of light, by the way. Sun's diameter, we get 4.6. 4.6 seconds for the sun to radiate its light the distance of its own diameter. Right? So you have, that's 1 second, roughly 2, roughly 3, roughly 4, and 4.6. How? There's nothing exists that radiates its light so slowly. I say that because this bulb, look, now we could do this every single day for the rest of eternity, and it's never going to change. Now the sun if the sun was condensed down to here and it turned on from off, it would go 1, 2, 3, 4.6, like there. 4.6 seconds to radiate its light, the distance of its own diameter. And again, and again. And 108 times is 8 minutes and 20 seconds. 108 sun diameters. And they're telling you that it takes 4.6 seconds for that monster to radiate its light a distance of its own diameter. Well, I don't think it does, and anybody who thinks otherwise is not looking at it properly. It's not what they're saying, it's the numbers, isn't it? It's ridiculous. Absolutely ridiculous. It's illogical and it defies common sense. It's not rocket science, is it? The sun taking that amount of time. Alexa, what is the diameter of UY Scuti?
UY Scuti's diameter is 2.377 billion kilometers.
One of the biggest stars ever discovered. I think there's bigger ones now, but in its day, UY Scuti. It's an I, it's supposed to be a C. UY Scuti, 2.37 billion kilometers its diameter, right? 2.37 billion kilometers. Alexa, what is UY Scuti's diameter again?
The quarter's diameter is 2.426 centimeters.
Alexa, what is UY Scuti's diameter?
UY Scuti's diameter is 2.377 billion kilometers.
2.37, we'll call it billion, right? Now, $299,792. UY Scuti is 2.377 billion kilometers. Right? 2.37 billion kilometers. Alexa, what's 2,377,000,000 divided by 299,792?
2,377,000,000 divided by 299,792 is approximately 7,928.8307.
7,928. Now what is that? That would be seconds. Sun's diameter, we've got 4.6. Alexa, what's 299,792 multiplied by 7,928?
299,792 times 7,928 is 2,376,750,976.
Right, so we've got 7,928 seconds. Let's divide it by 60. Alexa, what's 7,928 divided by 60?
7,928 divided by 60 is approximately 132.1333.
132. So we've just turned seconds into minutes. by dividing it by 60. Now if we divide that by 60, Alexa, what is 132 divided by 60?
132 divided by 60 is 2.2.
2.2. 2 hours and 12 minutes. 2 hours and 12 minutes. That is how long it takes for UI Scuti to radiate its light the distance of its diameter. At 2.37 billion kilometers in diameter, right? That's from there to there. It takes it 2 hours and 12 minutes to radiate its light, the distance of its diameter. 2 hours and 12 minutes. Well, I think you'll find that the size and power, right? It's ridiculous. Absolutely ridiculous. Light is absolute. Light is absolute. Light from the sun and the stars is absolute. There's no equation that proves otherwise. And all of this, right, saying that stars can't even, no. UI Scuti would just go bang from off and light up as far as it could instantly. And anybody who was even 1 billion kilometers away, look at the diameter, for crying out loud. Alexa, what is 2
I
billion?
missed something.
Alexa, what's...
Can you say it again?
Yeah. Alexa, what's 2... Alexa, what's 2,377,000,000 divided by 1,390,000?
2,377,000,000 divided by 1,390,000 is approximately 1,710.0719.
Right. That's UI Scuti. We're dividing UI Scuti by our sun. 1,390,000. How come my throat's going? Right? Into 2.37 billion. Just to double check. Alexa, what's 1,390,000 multiplied by 1,710? Oh, throat.
1,390,000 times 1,710 is 2,376,900,000.
There you go. 1,710 of our sun diameters in there. One 1,710. And when they radiate the light, they go. Joke. Honestly, it's a joke. I'm sure most of you can feel it. Alright, peeps. Laters.